So, hello. Wait, I need to set this. Welcome to Lambda Calculus. So yesterday I found out. So in the last one we've been reading the. Wait, I want to put some music. Actually, forgot to put some kind of music. Yeah, I put this actually right. This is kind of nice. Sorry about this. I usually set this before the stream. Oh, it's not showing it here. Interesting. Oh yeah, advanced properties. Vocaster. Yeah. Put this actually. So yeah, I was yesterday I looked again into the pairs, to the make pairs, the make pair function, and to put it, mildly, my mind was blown. Why? Because the make pair is so profound. So profound. What do I mean by that? Okay. So we're going to be looking into church pairs. I had no idea about this. So look, what happened yesterday? Okay, what really happened? What happened yesterday? So I really like how this series is going through. Let's go to GSCI. So, okay, again, what do we have so far? And I really like this approach. It's been going very slow, but it's almost like by the end of it, I will kind of understand what's been going on so far, right? And rather than going quickly through all the functions and understanding them in some very surface-like level, this is kind of very different what's been going on. So first we had the identity, right? The self-apply and the apply function, right? And I'll just write them actually quickly here because it's not a big deal, right? We had the id, right? And the id, for example, we apply the 2, we get back the 2, which was also like the basic combinator of sorts. And then we had this self-apply, the self-apply, which I actually cannot define here because it applies itself to itself, right? And then we had the apply function, right? Which was kind of, it's almost like a make pair. It's not a make pair. Okay, well, it's not a make pair, but it's kind of, and I like this progression from self-apply, to apply, and then to make pair. Because if we look, the self-apply has lambda, the self-apply has lambda SS, and it's all the same, right? There is an argument being applied to something, to an argument. But then with with the apply function, right, we got something else. We got the so we got the apply, and what did we really have? Lambda A. No, what do we have? Look at this. We had lambda F, right, and lambda A, right, and then FA. So it was almost like a step up. This was almost like a step up from the self-apply, right? Because now we don't have just like one lambda here, one head, and the argument being applied to itself. We have two things, and we apply one to the second. But now with the make pair, that was kind of weird. I didn't even get it at first. It's been already, a couple of days, but there's something strange going on with make pair. Because my naive idea at first is that make pair simply creates a pair. But how does it do it, right? Is it a tuple? Is it a list, right? Like, how does it actually create a pair? I mean, I guess when you first make this, you kind of have this naive idea that make pair will take two things and it will make a pair, but it's not. It's a function. But what does that mean, right? So make pair is lambda A. So it takes a thing, right? It takes a thing, and then it takes a second thing. And then, well, I guess you could write like this also. It's a function, well, make pair is a function that takes a thing and takes a second thing, right? And then creates a function, or it takes a function, you could say. I'm not sure what would be the right word. And then a function. And then that does what? What does it return? It returns a function. So we just have this thing calling a function and returning a function, which makes make pair a higher order function. So this is not just a function that is kind of working with values. This is a function that calls a function, okay? But still, so we have A and FAB then. But my naive idea was that I have A and I have B, and then I have to call a function, and then F being applied to some A and B will create a pair. And then what was very silly, I do make pair like hello world. And it gets me like this: no instance for show, string arising from use of print. And then you almost like, what's going on? Make pair. So it's not a concrete thing. It cannot make a pair out of these two things. It can make a promise that it will apply a function to some two things. What does that mean? I've been actually chatting with ChatGPT then, and it did help. It's kind of asking it, and FAB, because I would need to apply here. I would need to add something here. Now, you might try then, okay, could I do like make pair? And we don't have a plus defined yet, though, in our Lambda Calculus, right? I still don't have a plus defined. Not working. I still don't have a plus defined. So I thought then maybe I could do like make pair then plus because it needs some kind of a function. But wait a second, I cannot do make pair plus 1 and 2, right? It won't work. So make pair will make a pair, but then I need a different function. So then I thought, okay, first select. Do I have first select? First select, no I don't. First select is lambda A, lambda B, and it outputs an A, right? And the second select, lambda A, lambda B, B. Okay. So then I thought, well, do we do select first? Make pair. Select first, make pair. One and two. Do I do like this? No. Variable not in scope, select first. Wait, let's see if this works. Select first 1 and 2. Variable not in scope, select first. Did I really save it like this? Wait. No, I didn't. Wait a second. Let me do it again. Lambda A. Wait a second. Second select, first select. First select. I'll do it like in the book. Select first, lambda A, lambda B, A, and select second, lambda A, lambda B, B. So I thought then, do I do select first, make pair 1 and 2? No, it won't work. Then I thought, what is it? Is it something with types or what? Select first, make pair, hello world. No. But then you think, how am I applying the function? Like I'm applying select first to make pair. Do I have to do select first, make pair, hello world, maybe like this? No, it doesn't work. So then I go maybe make pair hello world, select first. Is it like this? It's like this. Make pair hello world, select first. So what's going on? I was confused by this. Yeah. Make pair, and then I learned about church pairs. Check this out. I had no idea about this. So church pairs, and look at this, see cons. So I know cons from Lisp, and also, okay, first I heard about cons in Lisp, but also in Haskell, right? So with cons, you cons things. Church pairs cons things. So you cons a list, you create a list, right? With cons. 1 cons 2 and so on. Just a comment. Wow, it's so weird. Interesting. Weird comments. So church pairs are the church encodings of the pair type. Church pairs are the church encodings of the pair to tuple type. So the pair is represented as a function that takes a function argument. So when given its argument, it will apply the argument to the two components of the pair. So it's like you read this and you get it, but it's and the pair here actually is defined a bit differently. Lambda x. Oh, okay, well, no, it's not. Wait, lambda x, lambda y, lambda z. Okay, we have a z instead of f. Lambda x, lambda y, lambda z, zxy. And first is, so then first pair AB. But look at this thing works. Why? Because that's the thing I did at first. Wait a second. Select first, make pair, right? Make pair AB. Will this, no, this will not work because I don't have a value, I think. I don't have a value provided. Let's do hello. Let's do like A and B. Yeah, why this doesn't work? Interesting. Wait, like this. So make pair. So okay, we have select first, and we're going to apply that. Let's try like this. Let's see what's going on. Make pair A and B. Yeah, but why is it showing an example? Select first, make pair AB. How would you substitute? Yeah, I'm not sure actually how is it going on. Let's see here. First pair AB. Okay. Lambda P. What's lambda P actually? Why is it this defined as lambda P? Because I don't have it defined like this. Lambda P dot P, lambda X dot X. Yeah, why is the pair? Okay, my pair was defined like this. Okay, let's try this. My select first from the book is defined as lambda A, lambda B, A. But in Wikipedia on church pairs, the select first is defined as lambda P, what's lambda P? Lambda P dot P, and then lambda X dot Y X. Right, it's the same thing, it's just it has this lambda P dot P. Lambda P dot P, lambda X, or let's say lambda A, lambda B, A. What is the difference? Just answer this. The difference lies in what is being passed as the input. Maybe that's why it can be applied at first. So books version, lambda A, lambda B, A. This is a function that directly takes two arguments and selects the first. Wikipedia's version, this expects a church pair as input. It applies the pair P to the selector function ABA, which retrieves the first element of the pair. Yeah. This expects a church pair as input. The book's version is the selector function itself. Wikipedia's version applies a church pair to the selector function. They are equivalent in behavior but different in context of how they are used. So is that the reason why when in my version, when I put select first pair AB, no, I should put like this, make pair AB, doesn't work. But when I put make pair AB select first, works. The behavior happens because of the order of application and how church pairs are structured. Your version select first make pair doesn't work. Select first in your version expects two arguments directly. It expects them directly. However, make pair AB is a church pair, a higher order function, and passing it to select first doesn't provide the two arguments A and B that select first expects. That's what I thought I'm doing. I mean, the naive me thinking that select first, the make pair will somehow create two things and select first will take the two things, right? I thought this is the same as when you do select first and then you have like A and B. So the select first will just take an A. But it's not what's going on. The make pair calls a function that it's kind of really subtle. A church pair like make pair AB is a higher order function that expects a selector function as its argument. When you write make pair AB select first, you're applying the church pair to the select first function, and it correctly retrieves the first element. I think we have to practice. Let's try it actually. So we have a make pair, and let's do hello world and do select first. And let's do it like this. Let's try actually to see what's going on, because we don't see it actually GHCI. It won't show us. It will just give us the hello, right? Right, if we just do make pair hello world and select first, we just get the hello. We don't see the steps. So what do we do actually? Do we substitute the function definition for the function name? Yes. Yes, actually we do. But where? Make pair or select first? Make pair, right? What's make pair? Make pair is lambda f, lambda a, lambda b, lambda f, fab, right? And then hello world, and select cell first, select first, select first. So what do we do now? FAB and hello world. Okay. Okay. So what do we have here? So look, we have a function here, right? And here we have some values, right? Or I guess you could say some arguments to this function. So let's go with the first one. Hello. Yeah, it's kind of tricky, like you almost want to substitute it for the f. Well, this is the function, right? Hello A, so that's the A, and the world is B. Well, let's try with the A. So we substitute here for the A, the hello, and we remove the head. So we will be left with a lambda B and lambda F, hello, and B, right? That's what we're gonna get. And I'll actually close this, right? No. And then we're gonna be left here with world and select first. The next step we're gonna do is we're gonna do the same thing with the world. So the world is gonna substitute the B and we're gonna remove the B head. So that means we are left with a function f, lambda f, and f, hello, and instead of the B, we're going to have a world, right? Isn't this cool? And select first. So lambda f, hello first, and now it makes more sense, right? So what are you going to do now with a make pair? We don't have a make pair. We don't have a pair. We have a, I'm not sure what would you call this? It's a promise or something like that, right? It's waiting. It's a function. It's so subtle, because this is the naive idea was the make pair will create a pair, some kind of a structure, but it's not creating a structure. It's kind of saying I will apply some function to these two things, right? It's not like here's your pair, but like I will apply something to these two things. It's almost like a very subtle, more subtle idea of a pair. It's not like here are two things, I just made them, and I'm like, what did you do with them? I just put them like this. Oh, why? It's like almost you have, yeah. And look at this, and now you will. Now I do select first, I substitute the f. So right, it needs a function. It's a function that applies a function to two things. And now the select first is substituting the f, right? And we're gonna get select first, hello world. And look at it. Select first will take the hello. But you might say, but where's my pair? It did create a pair, but almost like an intermediate kind of a thing. It's not like here's a pair. It's concrete. What are you going to do with it? I don't care. Here's a pair. No, it created a pair by saying, I will apply a function to these two things. What do you want me to apply? Well, apply, select first. Here's the first thing. And we get the first thing of the two. But we don't have the pair anymore. The pair is gone. It's so subtle, and I don't know, this is like I was like, wow. And then the idea, it's called church pair. So subtle. First pair AB. But it's just here, it's slightly different. What's happening here? His first pair, it's just first is applied with a lambda p.p, I guess. Lambda x, right. We are doing the same thing here, a and b. Lambda p.p x, okay, this stays the same. And this was substituted, right, for the a, lambda x, and for the b, lambda y. So it remained just with lambda z, zab, right. That's what we got, actually. And now, oh, it did the substitutions for the lambda p dot p, of course. But wait, lambda p dot p. Oh, yes, and lambda p dot p is a free variable. When you look at it from this scope, lambda p dot p is a free variable. So this is substituted. I guess this is just the one way how you would put first before the pair. Lambda p dot p is going to be substituted with this thing, and now finally we reversed it, yeah, as we started, because I didn't have a lambda p dot p, so I began with pair and select first. But if you want to do select first and pair, then you have to have a head so that you can bind it, but not a head that has some kind of a variable in the body, but it's just a head, lambda p dot p. Then lambda z, zab, lambda x, and the first. And of course, then the first substitutes the z. And we have the select first AB, and it selects the first. What an amazing thing. I don't know, it was just mind-blowing, this. And it's called a church pair, encoding the pair to tuple type. Cons, pair. And what can you do with pairs? You know, one idea is like maybe you could do everything with a pair. Like, could you create a list with a pair? Maybe, right? It will take really long time, but you could create a list basically. Because I did select first and then select second. Select first. Yeah, I'm still not sure. How would I create a list or something? And make pair. Hello world, make pair. List encodings. Mutable list. Oh, now he's doing the list here. This is church encodings. This chapter on Wikipedia, what is this? Value. Extract. Oh, look at this. Value container. What is this? Church encoding. It means representing data and operators in the Lambda Calculus and church numerals. So these are all like things that we take, you know, like in a more concrete way, but here they are represented as functions. Representation of the natural numbers using lambda notation. So Alonzo Church, yeah, the smile, who first encoded data in Lambda Calculus this way. Maybe he liked jazz. I don't know. Terms that are usually considered primitive in other notations, such as integer, booleans, pairs, list, and tagged unions, are mapped to higher or order functions under church encoding. Right. The church Turing thesis asserts that any computable operator and its operands can be represented under church encoding. In the untyped Lambda Calculus, the only primitive data type is the function, so they're all functions. It's amazing. So there is something now here about use. Church encoding is complete, but only representationally. Yes, additional functions are needed to translate the representation into common data types for display to people. It is not possible in general to decide if two functions are extensionally equal due to the undecidability of the equivalence. Oh, from Church theorem. The translation may apply the function in some way to retrieve the value it represents or look up its value as a literal lambda term. Lambda calculus is usually interpreted as using intentional equality There are potential problems with interpretation. Okay, that's now another deep subject. Church numerals, and we are going to actually define numbers. Look at this. I'm not actually reading this much, but how to define numbers and successor, addition, that's all we have to define. Multiplication, predecessor. So we are kind of creating a language with functions. That's why I'm doing it now. The more I do this, the more I'm sure, if you want to really get the idea of functional programming, you gotta learn Lambda Calculus. And it's so beautiful, actually, because it's so simple. And you create all these things that you don't expect because you take things, for granted. Make a pair, right? Here's two things, here's a pair. It's so simple. But when you look at it like this, division, look at this. Divide. Using lambda. Look at this. Is this division? Yeah. Like this, okay, this would be impossible to understand. So 9 divided by 3 is represented like this. Lambda f x f f f f f f f f x. This. You can read this, but the computer can. Plus and minus, multiply, divide, translation, types, church booleans. Well, that's what we did. True, false is basically the select first and select second. This is and or not. What a incredible thing, really, the make pair. And I chatted with ChatGPT about it, and it told me like I could define swap. How would I define swap? So make pair, hello world. I forgot actually, but you could like swap the values. Fascinating. Okay, let's move on, and then we'll come back to this. But it's just so wow. I was really wow. Okay, so now we reached the end of the chapter, and there are exercises now, and then conditionals, booleans, and integers. Interesting, because the definition of the booleans will be what we did, but he introduces them here. Well, yes, he introduces the booleans like and or not. And look at this conditionals. It's like, yeah, not. Okay. So let's practice now. Exercises 2.17, okay. Analyze each of the following lambda expressions to clarify its structure. If the expression is a function, identify the bound variable and the body expression. Analyze. So it's just to like analyze. If the expression is a function, identify the bound variable and the body expression, and then analyze the body expression. If the expression is an application, identify the function and the argument expressions, and then analyze the function and argument expressions. Now, if this makes sense now, because he's constantly repeating this kind of language, and we have been trying to read it like that. So we have a function, right? I'll do it like this. So we have a function here, lambda a, right? And this is the body, a, lambda b, ba, right? clarify its structure. Well, we have a function with this body, right? And this thing itself consists of what? A lambda b dot ba. Well, the a is a free variable. If we look at this scope, this a is not the same as this a, right? So this is free and this is bound. This a is bound. Well, no, actually, interesting. This a is bound with this a, and this a is free. I don't think this is, yeah, it depends, right? That's what we were saying about the namings. This a is free, actually. So we have a lambda b dot ba. Right? Lambda a dot a, lambda b dot ba. And we have two lambdas here, lambda a and lambda b. But this lambda b is inside. This is not the same scope. This is the outer lambda. This is the inner lambda. You think we could solve this? Maybe we could try to solve this. So let's try to solve this actually. Lambda a, we have a dot, so we put this, and then what? A, and then we have a lambda b, and we have this, and then we have a BA. Right, so let's do, let's apply maybe X and Y. Or that's too confusing. Maybe do 1 and 2. Yeah, maybe do 1 and 2. So could I substitute? Yes, I could actually substitute A with 1 and 2. But he didn't, the exercise isn't about solving it, you know. But you could actually, yeah, substitute. Let's do actually here, hello world. So we substitute the hello with the A, and we get hello, right? And then BA. No, what am I doing? We have a lambda B, BA. Like this. Hello BA, and then world. So now we have hello. So we could substitute the B, A. So we do world A. So yeah, we have hello world and the free variable A. And analyze. Okay. The second one is, yeah, will be hairy. Look at this. Okay, lambda x, lambda y, lambda z. Okay. And zx, zy. Well, we have 3 lambdas here, right? Lambda x, and this is the body, right? And then we have this head with this body. And we have this head with this body. And inside we have the z that is bound, we have the x that is bound, we have the z that is bound, and the y that is bound. Now this z and this z is in the same scope. So z is applied to x and the z is applied to y. Yeah, it's kind of nice. This thing works. you know, let's try it. So if we do hello world, world, so we substitute the x and the y. So the x will be hello, right? The hello will substitute the x, lambda x, and x is here. So we're going to do lambda y, or let's go step by step or not. Let's actually, we don't have to do it. So I will substitute the x for the hello and the y for the world. That means we'll have a lambda z, I'll do it like this, lambda z, and now zx, x was, we said hello, and then we have a z, and y is world. And that's it. Well, we can drop this now because we don't have a, oh, hello world. Yeah, actually hello world would, why are we supplying only two things? Hello world and boom. No, okay, boom. Haha. The z will be haha. And then we substitute the z, so we get the haha hello, and we get haha world. Haha hello, haha world. Okay, that's not hard though. Okay, here we have the same thing. Lambda f, lambda g, lambda h. GH f, lambda p dot, lambda q, lambda p. This is more complicated. Lambda f, lambda g, lambda h, gh, f, and lambda p. Yeah, you kind of, maybe you kind of also wonder, is this lambda p at the same level as lambda f, or is it at the same level as lambda h? Interesting. Okay, so check this expression and show the inline outline in one code block. Okay, I said show in one code block. And he's going to apply this too. Oh. And he's going to simplify it, yeah, because you cannot actually simplify it anymore. No, I thought just, no, he didn't do it at the end, you see. No, show me the nesting and the scopes in one code block. Don't solve it. Let's see now. Okay, first scope F, right. Lambda G is the second scope, lambda H is the third scope, nested within G and F, right. Now, inside of the lambda H, you apply G to H, right. And the G from here is bound here and H bound here, right. And the F, apply result to F within scope of F, right. But then you close this and new function, but it's true, lambda p is not on this scope level, it's on the lambda h level, so on the third level. New function p, lambda q, and p from here, and that's it, right? Actually, that's true, okay. Now the fourth thing, phi, I think this is not three things, this is just fee, phi, fo, fum, fo, fi. It's just using, I guess, different lambda phi, lambda phi. I guess I'll say phi, phi, pho, fum, pho, phi, fum, pho, phi, phi. So 1 level, 2 level, 3 level, 4 level, free variable compared to this scope, but bound to fum, and inside, well, it's not inside. Fum is being applied to pho, is being applied to phi and phi, but it's, the parentheses are not the same. So it's phi is being applied to this is being applied to this, and fum is being applied to all of this. Are they all bound? Fum, pho, phi, phi, they're all bound. Okay. Lambda p, lambda q, p, lambda x, xp. P, okay, we don't have free variables. Lambda x, lambda I, together with lambda x, and lambda q. No, together with lambda x and lambda q, right, together with this level is the lambda I. Even though we have 2 lambdas here, but they're on the same scope because we don't have a dot between them. Otherwise, we'd have a dot. Lambda I, lambda j, and ji, right? That's not hard. Evaluate the following lambda expressions. Evaluate them. Okay. Evaluate them. Let's evaluate them. Lambda x dot, lambda y dot, yx. Okay. And then on the same scope with lambda y, we have lambda p dot, lambda q, and p. Okay. And then lambda I dot I. Lambda I dot I is actually the identity function. Identity function. Wait, I want to change fonts just for the fun of it. Font in Kitty on the, how do I change font? Yashevka. Change it within the term. I think I can change it within. Only for the current session. Really? Yoshevka. Can I change it with kitten? Kitty kitten fonts. Kitty kitten fonts. Really? Kitty kitten fonts. Okay, I won't do it now. No, I just want to change font. Kitty kitty set font. One second, let me try something. Nope. Will this work? Not a known command. Okay. Kitty kitten font. So much, and it's kitty kitten font. No kitten name fonts. Yeah, whatever. It's not working. Um, let's get back to this. Concentrate. Evaluate the following lambda expressions. Right. We have it here. Lambda x. Well, this is just the identity function. And identity function, it's here. I think we have to first apply this and substitute for the lambda x and lambda x. Right? That's it. What else can we do? So we're going to have a lambda y. A lambda y. I'm going to be y lambda I dot I, and then lambda p dot lambda q dot p. Yeah, and now what do we have? Lambda y well, I guess you could, maybe we could apply this actually, because this thing is being applied to this. We could substitute this actually. And let's keep the dots because it seems it's more complicated without the dots. Maybe we could apply this thing here inside of this definition, and then do the identity later, and then we'll check actually how do you do that. So lambda p, really, lambda p lambda q dot p. Yeah, I'm not sure. Well, like you could define identity. You could do this identity and substitute it here for the lambda p. So then you'll have, you know, lambda q lambda I dot I, and then this thing can be applied here. Or maybe let's stay here inside and do this with the lambda x. So we're going to have a lambda y dot and then y, and then instead of the x we're going to have a lambda p dot lambda q dot p, and outside lambda I dot I. And now we're going to substitute lambda I. So we remove the lambda y hat, and instead of the y, we're going to have the lambda I. And we are going to apply that to lambda p dot lambda q dot p. Right? And that's what we have. And now what do we have? We just have lambda p dot lambda q dot p. And we're done. Yeah. Lambda p lambda q p. How would you evaluate this? Oh, not this. Okay, sorry. Evaluate one of the following lambda expressions. I mean this. Outer application. Is it doing the outer application? Lambda I. This is the outer application, right? Here lambda x dot y is the function being applied to the argument lambda p, lambda qp. Okay, that's clear. Substitute lambda p for x in the body. That's what we did. After substitution, we get lambda y, lambda p, lambda qp. Yes, that's what we got. And next application. The resulting function lambda y, lambda p, lambda qp, right, this one, what we got, is now applied to lambda I dot I, right, now applied to this. Now substitute lambda I dot I for y in the body, that's what we did, we get this, we get this. Simplify this application, apply lambda I to lambda p, since lambda I dot I simply returns its argument. The result is lambda p, lambda qp, that's what we got. Final result, okay. That's what we got. Evaluate the following lambda expressions. Let's do the second one. Okay, so these are actually exercises. 2 point. Maybe I should just write it here, exercises. 2 point something. So what's the second one? This one is longish. What do we have here? Lambda x, lambda y, lambda z, and then inside we have this, and then lambda f. This is on the same level as this. Lambda f dot lambda a, f a. This is our apply function here, right? Look at this. This is our apply function, and this is our make pair function. Interesting. Look at this. X, Y, Z. This is our make pair function. This is our apply function. And this is our identity function. And this is also another identity function. But here it's just written with J and here with I, which is basically alpha. Conversion makes this the same, right? Lambda I, same as lambda J. It's just a different, but it's just identity. So what do we first do? Wait, we apply. Well, this is being applied to this. And then we're going to apply this to something inside and then this to something inside. So let's first apply the apply to the make pair. So we're going to apply this whole thing and we're going to substitute it for the lambda x. So we're going to get a lambda f dot lambda a dot fa instead of lambda x. And then we're going to have what? Lambda y dot lambda z dot, and well, we're going to have just y here and z. So that will be our first thing. And outside of that, let's close this. Let's close this. And outside of that, we're going to have from before lambda I dot I. And well, let's close that too. Let's close that too. And outside of that too, we're going to have a lambda j dot j. So now what do? Now we do lambda I dot I. We substitute for what? No, we still have two things now here. We have two things here now. Look at this. Lambda f, lambda a, fa, and lambda y. So we should substitute these guys now. This should be go inside of f. So we're going to get lambda a dot, instead of f, we're going to get lambda y dot lambda z dot y z, right? That's instead of f. Lambda y, yeah. And this being this being applied to A. Yeah. We close this. So lambda A, we basically removed this F. We substituted this whole thing for the F. So we have lambda A, so we remove the head. So we have lambda A dot, this whole thing again, and then A, right? And then outside again, we have lambda I dot I, and lambda J, J dot J. So what do we have now? Lambda A dot, lambda Y dot, lambda Z dot, YZ applied to A, lambda A. So now we have to start with lambda I. Lambda I is going to substitute the A. So we're going to have lambda Y dot, lambda Z. We just copy this out, YZ. And instead of A, we're going to put lambda I dot I. And outside of that, we're still going to have lambda J dot J. Right? That's what we have now. Lambda Y dot, lambda Z dot, YZ being applied to lambda A dot, lambda I dot I. And outside of that, I didn't put the parentheses, lambda J dot J. Maybe I should have put it right, because YZA. I should put it. It will make more sense. Like this. But now you could say, if we substituted the lambda I with the lambda A, lambda J, we could substitute now lambda J with the Y. So get your lambda Z dot, and Y will be lambda J dot J Z. Right? I should have put the parentheses before. And now we have lambda I dot I. But don't I just now apply? Actually, I have to apply lambda I. Really? I do apply lambda I instead of Z. It's almost like calling me. Yeah, I'm not sure. Let's try it. Because then I'll have lambda J dot J being applied to lambda I dot I. Which is just another identity. Well, it probably makes sense that all of these guys are value to a single identity. Try this. Okay, first application of lambda x, lambda y, lambda z. Substitute fa. Right, that's what we did. We first this substitute with the lambda x in the body, right? And then we get lambda y, lambda z. We get this, right? Second application to lambda I. That's what we did. Substituted for the y. Exactly. So lambda z, fa, lambda I, z. Where's the lambda j. Oh, he's still inside. Simplify this now. Lambda a, lambda I dot ia. Did we had? I think I actually messed up something. Yeah, in the process. Yeah. What did I mess up? Lambda a. Simplify lambda f. Let's evaluate the step by step again. Oh gosh, this one is kind of... But these things are important. These things are important. Trying to motivate. Lambda x dot lambda y lambda z. Yeah, we substituted this for lambda x. We get lambda f, lambda a, fa. Lambda and then we get lambda y, right? Oh, I did a whole... This is horrible. Ah, I should have removed the head. What did I do? Completely wrong. Oh. Wow. Fascinating. This was all wrong. So I didn't delete the head. I put the expression inside of the head that I was supposed to remove. And I didn't put it here. So weird. So right. So we need to substitute this thing for the x. So we remove the head. We remove the head. So it means we have lambda y dot lambda z dot, and inside we're gonna get lambda f dot lambda a dot fa. Oh, this is going to become really fa. And this was being applied to y and to z. And then outside of that, we have a lambda I dot I, close brackets, lambda j dot j. Okay? Now it makes sense. Now it makes sense. That was the mistake. And now what do we have here? Yeah, this is becoming already really hard to read. But it's not just hard, it's like pointlessly hard. Lambda y, lambda z, fa, y, z. So now we're going to apply lambda I dot I instead of y. I guess there's nothing else to do. And then we're going to apply lambda j instead of z. Let's do that in one step. So we're going to substitute lambda I dot I for the y and j for the z. So that means we're going to be left with, let's do it first without lambda f. Wait, we have one. Lambda f dot lambda a dot fa, right? And outside of that, we're going to have a y. And y, we said it's going to be what? Lambda a, lambda I dot I. And outside of that, we're going to have a z. And we said z is going to be what? Z is going to be what? It's going to be lambda j dot j. So now we have an f, lambda a, fa. We have our apply function, and I, and j. So we could basically substitute I for the f and j for the a, which will leave us funny, we get the same result. We get the lambda I and lambda j. Yes, we're just gonna get, you know, lambda I dot I being applied to lambda j dot j. Probably gonna have the same thing. Lambda a. Simplify lambda I a to a. Lambda I. Lambda a. Oh, it didn't have the same result. What did he do? Okay, he did the same thing. First application. Substitute for x in the body. Right, that's what we did. And then second application. Did he apply I and j? Of lambda y to I. Then he substituted the i's for the y's and j's for the z's, I guess, right? Where is the j? How come I don't see the j? For the z's, yeah. The result of evaluating the expression is lambda j. Apply z to j. Since zz simply returns its argument, the result is lambda j. Oh, right, actually. Lambda, this was the mistake, right? If we did lambda I dot I and some value 2, well, we would just drop this whole thing and leave 2, because the identity function returns whatever you give it to. In our case, lambda I dot I returns another identity function. So result is not 2 identity functions, but just one, lambda j dot j. We have the same result. All right. Well, this is going fine. Lambda, how long has this been going through? 1 hour and 17. Okay. Let's see, stream, 1 viewer. I'm never sure what that means, 1 viewer. Is that like me? Is that like me, or there is actually 1 viewer? Yeah. So now we're going to add the third thing. Evaluate the following lambda expressions. Okay, the third thing now. This practice is important. Okay. Lambda h and then lambda a dot lambda f dot fa. H. Okay, so this thing now is it being applied to this thing? Oh, look at our old friend self-apply function. So the self-apply function, it's going to substitute the h. Oh, interesting. What's going to happen? Well, if we do that, we're going to get lambda f dot, I'll just do like this, ff, lambda a dot lambda f dot fa, h is lambda f dot ff, and then another h, lambda f dot ff. I just substituted it. But now what do I do now? No, again I did the silly thing. Gosh. I put it in the head. It's like this. We substituted the h So we have two things here. So we have this thing and these two things. So now we're going to substitute I'm actually not sure because it's all on the same level, this thing. Let's try. Try this. Lambda h lambda a, lambda f, fa. Yeah. So the outer application, the function lambda h is applied to lambda f dot ff. Substitute lambda fff for h. That's what we do. We get this expression and we get the two self-application functions outside. Evaluate the inner application. And then we have to do the inner. The function lambda a, lambda ffa is applied to lambda fff. Well, substitute lambda fff for a in the body. Okay, so it does that. Lambda ff, lambda f dot ff. And replace the inner function in the remaining expressions. Now the expression becomes this mess. Apply. Okay, now we apply this too, of course. Substitute lambda fff for f, and we just substitute it, and there are a lot of f's, and we get this. Self-application. Yes, here is a well-known form of divergent combinator, like the omega combinator in Lambda Calculus. When evaluated, it leads to infinite recursion. Lambda fff, lambda fff. Oh, interesting. A well-known form of a divergent combinator, like the omega. Does this combinator have a name? The combinator you've encountered is often referred to as omega. Oh wow. It is a well-known example of a divergent combinator, meaning it does not reduce to a normal form and results in infinite recursion. Omega